Well, we're going to explore the existence of a creator that's beyond the constraints of time and space. The fundamental dilemma is that our universe that we see through telescopes or microscopes, whatever, is either infinitely old or it suddenly emerged out of nothing. And there really is no third option. When we're kids, we often ponder these kinds of questions, but then as we go through life and start getting preoccupied with just the day-to-day tasks of living, these things can recede back into the background. But this is basically a fundamental issue that all of us, whether we really think about it a lot or not, have an opinion. Is the universe infinitely old, or did it just emerge out of nothing? The classical paradigm is that we have an eternal universe. Plato, Aristotle, and many, many other writers have presumed that through the ages. There are a few exceptions, of course. Al-Ghazali at the turn of the first millennium and Thomas Aquinas, each in their own way, advanced a cosmological argument that implied, first of all, Al-Ghazali argued that an infinite regress of time, infinitely, is impossible. If there's an infinite regression of time, you never get to today. You saw that too, didn't you? Yeah. Okay. All right. If you read the writings of St. Thomas Aquinas, you also know that he also advanced arguments in the sense that things that are in motion can't move on their own. Objects cannot initiate their own movement. But both of these, those are arguing for God, which of course they were, are also embracing the concept of a finite universe. This is a minority opinion, and what is interesting today, and one of the great discoveries of modern science, modern physics, is that we now know our universe is finite, not infinite. And that insight has profound implications for all of us. Our universe is specific and it's unique. We also, scientists now hold the view from all kinds of evidence that it's an expanding universe. We've all heard about the red shift or the fact that the universe is expanding. The implications of that, among other things, is that if it's expanding, it had a beginning. And we'll go through that here shortly. The other thing we're going to discover is that it's a decaying universe. It's winding down. Now, these are discoveries of the last century. Part of the implication of 20th century physics is that we have a finite universe, it's expanding, and it's also decaying. So all of these things, first of all, underscore that if all that's true, it had a beginning. So I want to talk briefly about the implications of modern physics without getting bogged down in all the details. Albert Michelson, Naval Academy, class of 1873, incidentally, I have to work that in, and Morley did an experiment in 1877 that shocked the scientific community. Because on the one hand, they recognized light as a form, an effect of electromagnetic radiation, but they also assumed that it would pick up the speed of its source. Michelson and Morley went through great lengths to demonstrate that it's isotropic and it is independent of the speed of the source. In other words, the speed did not vary whether you're moving towards the source or away from it. And that is very, very difficult to visualize in terms of the models that were extant in that time. About that same time, just not many years later, Dr. Albert Einstein, in effect, launched a revolution that we are still exploring the ramifications of today. In 1905, he published his special theory of relativity, and that startled the scientific world because he was the one that, in trying to reconcile the implications of Michelson, Morley, and so forth, came to the conclusion that length, mass, velocity, and time are relative measures, not absolute measures. They all relate to the velocity of the observer. And that was a special theory of relativity, and we'll come back to that in a minute. And it was in 1915 that he broadened his declarations to what's called the general theory of relativity, which has many implications. But one of the most profound things, and I believe it's one of the most essential insights for anyone that's taking the Bible seriously to understand, because it's amazing to me how many theological controversies, on the other side of the fence, so to speak, evaporate if one really understands the physical nature of time. But one of the things Einstein pointed out is there's no distinction between time and space. That's a strange idea for most of us unless they're specially trained. In fact, a professional typically will speak of space-time. They're a continuum. We live in at least a four-dimensional continuum. Actually, we'll come back to that, but from Einstein's perspective, there were at least four dimensions. While there are some people even today challenge some of his views, pretty much it's gotten broad acceptance by many, many different approaches, at least a dozen of them, and it's been confirmed, the precision of his mathematics has been confirmed beyond experimental error. So, now, to give you an insight that may be helpful, if you examine a triangle, all of us in school have, at one time or another, wrestled with triangles or trigonometry. And if we add up the angles of a triangle, how many degrees does it add up to? 180 degrees. And whether it's a 30, 60, 90 or a 45, 45, 90 or any triangle, if you add up the angles, we all know it adds up to 180 degrees. What happens if we go outside with a transit, lay out on a large field and lay out a triangle, very large triangle, and we add up the angles and it adds up to more than 200 degrees? What would you conclude? Missler screwed up again, probably, right? The curvature of the Earth, absolutely right. You see, if you take a course in navigation, one of the things that you'll encounter is what's called spherical trigonometry. And you quickly discover that on a sphere, you can have a triangle with 90 degrees in each corner. And so this little rule that we all learned about a triangle has to do with a universe of only two dimensions called plane geometry. In a plane, a triangle always adds up to 180 degrees. But if you have a triangle with more than 180 degrees, your first insight is that you are no longer in just two dimensions. You've encountered the effects of an additional dimension. And in this case, a third dimension, a sphere. And it's that kind of an insight that caused Dr. Einstein to recognize that we live in more than three dimensions and that time itself is a physical property. Time itself varies with mass or acceleration or gravity. An example of that is atomic clocks. If I had an atomic clock here on the platform and I raised it 1 meter, it would speed up by 1 part in 10 to the 16th. Now that's not enough to adjust your personal schedules, I don't think. But it's interesting that it's predictable. If I move it 100 meters up, it will speed up by 1 part in 10 to the 14th, and so on. Now, they actually have conducted experiments to verify this. Oh, incidentally, on the atomic clocks, the atomic clocks at the Royal Observatory in Greenwich, England, both there and at Boulder, Colorado, at the National Bureau of Standards, both use clocks that are accurate to about 1 microsecond per year. And the atomic clock at Greenwich, England, and the atomic clock at Boulder, Colorado, by the English government and the U.S. government respectively, are off by about 5 microseconds because of the difference in altitude about 1 mile up. The point is that this physical property of time is measurable and has to be allowed for under many conditions. The United States Naval Observatory in 1971 actually put atomic clocks on an airplane going around the world, one eastward that lost 0.06 microsecond relative to one at rest. And they put one on a plane going westward around the world, and it gained 0.27 microseconds, exactly what Einstein would predict from his equations. Now, if you get into this area in any textbook, you'll also discover that they generally will talk about 2 hypothetical astronauts. And we're going to send these hypothetical astronauts to the nearest star, Alpha Centauri. The astronaut that we're going to send to Alpha Centauri and back, we're going to send him at half the speed of light. Alpha Centauri is 4.5 light years away. He's going to go at half the speed of light, so it takes him 9 years to get there. And in the time that he ages 9 years, his twin brother on the Earth is 11. In other words, it's actually about a little over a year and a half difference if you go through the calculations. The point is, if he goes on a round trip to Alpha Centauri and back, when he gets back to the Earth, he's more than 2 years younger than his brother. Let me take a more extreme case of that. Let's put him at the rate of 99.99% of the speed of light. We're going to just send him one way this time. He's going to go to Alpha Centauri, and on his clock, on his spaceship, it took 4.5 years to get there. During that period of time, the Earth would have aged 318 years. So if he comes back he's going to discover 6 centuries have gone by. Now, obviously, there's all kinds of problems with this because it'd be pretty hard to get a guy going 99% of the speed of light. But the point is, they're intended to demonstrate, to raise the fog in our thinking, to recognize that time dilates, as they say. That time is relative to velocity of the observer. And it's important to recognize this because when you start talking about 15 billion year universes and you're talking about a 6-day creation, you've got to ask the question, whose clock are you talking about? What was gravity at that point? What was the velocity at that point? You have to recognize that time is relative, not absolute. See, you and I suffer from a misconception that we got from school. We went to the blackboard and the teacher made us draw a timeline. And we drew a line on the blackboard, say from left to right. At some point on the left was the beginning of something, the birth of a person, the founding of a nation, what have you. The right end of the line, or some place further down, would be the end of that nation or the death of that person or some other milestone. And it's comfortable for us to visualize time as being linear and being absolute. Now, we've just learned from Einstein that it's not absolute. But when we think of time and we encounter the concept of eternity, we generally assume that's like a line that starts at infinity on the left and extends to infinity on the right, whatever that means. And the trouble with that is a misconception. When we encounter the concept of God, we tend to visualize someone who has lots of time. Well, the question is God subject to gravity? Is he subject to the constraints of mass? You don't visualize God accelerating. He's omnipresent and so forth. So God is not somebody who has lots of time. God is someone outside the dimensionality of time altogether. And that's what Isaiah means when he says, it is he that inhabiteth eternity. For thus saith the high and lofty one that inhabiteth eternity. Now, if God has the technology to create us in the first place, he has the technology to get a message to us. One way he authenticates his message, one way he proves that it's not a fraud or a contrivance, is that he demonstrates that he alone knows the end from the beginning, that he can authenticate his message by demonstrating that its source is from outside time. And some of these sessions we're going to get into will be going into this much more detail. But as Isaiah again says, declaring the end from the beginning and from the ancient times, the things that are not yet done. The Bible is the only holy book on the planet Earth that has valid prophecies, that are precise, that are accurate, that are demonstrated throughout history. And one of the reasons this is such a hot topic for all of us this day is because you and I discover now that we are being plunged into a period of time about which the Bible says more than it says about any other period of time in human history, including the time that Jesus walked the shores of Galilee or climbed the mountains of Judea. But let's get back to 20th century physics. One of the things that's been going on in astronomy for the last 100 years are all kinds of discoveries that, strangely enough, are dragging the astronomers kicking and screaming into the view that, first of all, we got a finite universe, not an infinite universe. No matter how hard they've tried, they don't like a finite universe because that implies it has a beginning. And to face the beginning, that raises all kinds of other questions. But there's all kinds of evidence about an expanding universe. There's all kinds of evidences that they can infer from galactic motion, from proton decay, the nature of time itself that we've touched on, the nature of matter, big subject, and from that, the whole existence of hyperspaces. And we'll just touch on these things briefly. In 1913, it was discovered that galaxies are moving away from us. In 1915, Einstein, in his theories, clung to a concept. He created a fudge factor, which he called a cosmological constant. And he adjusted that number so as to imply that the universe was steady state, a steady state model. This was corrected later, and Einstein admitted later it was the biggest mistake of his career, his so-called cosmological constant. He didn't want to face the true implications of the fact that space is expanding. The fact that space is expanding implies it had a beginning. As we go through these various discoveries in astronomy, what's interesting is that people, if they're honest and open and look at this in an unprejudiced manner, are being drawn again and again back into the cosmological model that the Bible deals with. For example, there's a number of other ways I'm going to show you that space is expanding, quite apart from the classical redshift issues that everybody talks about. But it's interesting, throughout the Bible, you'll find these references. It speaks of God who alone stretches out the heavens. When you and I encounter that, we often think, well, it's a poetic figure of speech. But in Psalm 104, stretching out heaven like a tent curtain. That kind of phrase again and again in Isaiah, who stretches out the heavens like a curtain and spreads them out like a tent to dwell in. And you can find over a dozen other examples of this kind of expression. It's interesting that on the one hand, you find no cosmological errors in the Scripture, and on the other hand, you find it anticipate virtually all the discoveries of recent years. In fact, some of them really quite surprising. One of the things that you quickly get drawn into if you do serious reading in this area gets into the field of astronomy and the motion of the galaxies and all the inferences people draw from those. And the more you study them, the more questions they raise. But the fact that motion is observed throughout the universe is something that was observed literally over 1,000 years ago. That's Al-Ghazali's arguments were built on the fact that since there's motion, he knew, without knowing the laws of Newton, he knew that things do not move on their own. They're caused to move. And the fact that galaxies are in motion in the first place implies that something put them in motion. Objects do not move on their own accord. And since they can initiate motion, and the fact that they are moving implies that something happened. Something gave them a beginning. Physicists, as they get into the part at the other end of the extreme, in the subatomic particle world, there are many, many discoveries, and we'll touch on those in another session in a little more detail. But just to touch on one, there's a issue of the proton. The proton is believed to consist of at least 3 quarks, a subatomic particle, which decay irreversibly into all kinds of other parts, but it's irreversible. It decays. It doesn't happen very quickly. They decay into pions, positrons, and also some electromagnetic radiation. This occurs very, very slowly. But the point is, it means that matter itself is not eternal. That matter left alone decays into energies that contribute to the ambient energy of the universe, or increase to the entropy of the universe. But the fact that protons decay is disturbing because it's another irrefutable evidence that matter is temporary. Now, in recent years, Stephen Hawking and Roger Penrose, George Ellis, probably the best-known writers in this area, they have really gone further to probe the implications of what we know from physics, that space, matter, and time are irrevocably coupled. And all 3 of them had a beginning. Now, for us to imagine matter being created, I guess in our imaginations we can visualize that. Most of us have no capacity to imagine space being created. Most people who read about Big Bang models and such things assume that whatever's going on went to fill empty space. No, space itself had a beginning. The other thing that's difficult for us to understand is that time had a beginning. That's a very difficult thing to grasp until you realize that time is itself a physical property. Now, what's interesting to me, if you read the writings of 2 ancient Hebrew sages, very venerated sages in the Talmudic tradition, Maimonides and also Nachmanides, both wrote in the 12th century in Spain, in what's regarded by many as the peak of the Talmudic era. But if you read their commentaries on Genesis chapter 1, you'll discover that they determined from Genesis chapter 1 that matter, energy, space, and time each had a beginning. And I think that's fascinating. Nachmanides also had another insight we'll come to shortly. It's interesting that the Bible, all through the Scripture, describes the fact that time had a beginning. And that idea is very new, very revolutionary to most of us. Even science has had a tough time coming to grips with the implications of that. And yet when you go back and just take one example, 2 Timothy 1:9, speaking of Jesus Christ, who has saved us and called us with a holy calling, not according to our works, but according to his own purpose and grace, which was given us in Christ Jesus before time began. Now in your King James, they'll say before the world was, but if you look in the Greek, the word is chronos, time, before time existed. And there are many, many other examples, but this will serve our purpose for this time. Now, One of the things, if you get into modern physics, you quickly discover we know that matter and energy are the same thing. Anyone that's read about Hiroshima or atomic bombs knows that you can convert mass into energy at rather attractive ratios in the sense of being very, very powerful. But most of us have a tough time visualizing space and matter related. And that's what makes this area difficult on the one hand to deal in without mathematics and such, and yet it's so fundamental to an understanding because all these discoveries, all these insights confirm the Bible, the biblical view. The new paradigm that is emerging out of 20th century physics is shattering. And it's a refutation of most of the beliefs that you and I have been inculcated with in school. And biological evolution is but a small part of it. Matter, in a sense, is viewed as an interruption of space. It's related to the curvature of space. The one way to remember the relationship is matter tells space how to curve, but space then relates to matter how to move. And once you understand that matter and space are physically related, it resolves this strange enigma that thinkers have wrestled with for centuries, is how can a planet at a substantial distance from, say, a star, a sun, gravity holds it in an orbit, but what's physically there holding it? There's no connection, there's no waves, they've searched and searched, and it isn't until we really understand the nature of space that those things start to get resolved. We'll come to that a little further in a minute here. One of the most fundamental areas in science is embodied in the laws of thermodynamics. The laws are well established for the last 125 years in the field of thermodynamics, but it turns out the implications are far beyond just thermodynamics. The first law of thermodynamics, as it's called, law of conservation of matter and energy. While matter and energy are interchangeable, that's like changing the form of it. You cannot create it or destroy it. It's impossible to destroy matter. It may disintegrate into other forms of materials, but matter and energy can be converted. In fact, the conversion factor is Einstein's famous equation. People that know nothing else about Einstein all know about E equals mc squared. The energy is equal to the mass times the speed of light squared in all the right units. And that's why a little bit of mass at a place like Hiroshima or Nagasaki or wherever can yield such incredible energies. The law of conservation of matter and energy, in effect, says there's no way you can win. There's no way to create matter or create energy. All you can do is change its form. Second law of thermodynamics is probably the most important law in science. And it's called the law of entropy, or the bondage of decay is another way of saying the same thing. The way it's usually expressed in thermodynamic terms is that any heat process is less than 100% efficient. Throughout all fields of science, with the exception of the field of biology, the biologists have chosen to close their eyes at this, because if you accept this, it totally destroys any possibility of biogenesis or what they call evolution. But let me set that aside as a special case that Mark will be dealing with in one of our subsequent sessions. The second law of thermodynamics says that every heat process loses something to the ambient universe. That every engine of any kind operates on a temperature difference. But as the universe continues, every process is less than 100% efficient, which means it's winding down. There's no way to get more out of it than you put into it if you're examining the total package. Now, what's interesting, this is from the observation and understanding of the second law of thermodynamics that we realize that the entire universe is like a clock that's winding down. And it's only under local, very strange circumstances it might appear to be increasing, but that's, in a sense, a distortion from the outside. The entire universe, as a closed system, is winding down. Now, the obvious philosophical implication is, who wound it up in the first place? One of the great mysteries that serious thinkers grapple with are to try to think of what the alternative answers are to that enigma. And obviously for you and I, it's a glib answer. But the truth of the matter is, we have a universe that is finite and that it had a beginning and is winding down. By the way, there is a third law, and that's that entropy is zero at the absolute temperature of zero. So they often say that the first law says you can't win. The second law says you can't even break even. Third law says you can't get out of the game. But we'll move on. Now, this conservation of matter and energy is all through the Scripture. Such simple statements as in Genesis chapter 2, on the seventh day God ended his work. His creation was finished after those 6 days. All kinds of other implications going on, all kinds of intervention by God in what's going on, no question about it, with the flood and other things. But the point is, his creative work, everything was finished then. And Hebrews 4 emphasizes this. It says, the works were finished from the foundation of the world. And Nehemiah, all the things that are therein, that is in the universe, you preserve them all. And you realize that if you study the Scripture and you get the cosmological view of the Bible, it's interesting that science has been dragged kicking and screaming into a position that in effect confirms what the Bible has been saying all along. The Bible also talks about the decay. It says the earth is winding down. They shall perish, but thou shalt grow old as a garment in Psalm 103. The earth will grow old like a garment in Isaiah 51, very similar expression. Jesus says, until heaven and earth will pass away, but my word shall not pass away, and so forth. So we find this view all through the Scripture, if you're sensitive to it, that the world is winding down. Now, let's take the simplest example of this, called thermal decay. We know that energy transfers from the hot body to the cold body. It always flows from hot to cold, right? If the universe was infinitely old, it would be at a uniform temperature. In fact, the physicists would argue that it would seem that the boundary condition of the equations is when all temperature is uniform in the universe, it dies out. They call that a heat death as in a model. But since the universe isn't uniformly cold or uniform temperature, therefore it's not infinitely old. In other words, this is another demonstration that the universe had a beginning. Every time you see something hot or cold, it's a demonstration that the universe is not infinite. It had a beginning, it is winding down, but it ain't there yet. These dilemmas posed to physicists and mathematicians and cosmologists that we've just laid, the fact that it had a beginning, that it is expanding, and yet it is decaying at the same time, has led physicists to attempt to put together a model of all that we know in some consistent form. And because they've reluctantly had to accept the idea that there was a beginning, these models have a collective term called the Big Bang. And many people mean very different things when they talk about the so-called Big Bang. It's just a category of models attempting to reconcile what we think we know from the physical universe. And the early models, typically emerging in the 40s, dealt with a steady-state view of the universe, and they were quickly refuted. Even Einstein's biggest mistake of his career was his attempt to cling to a steady-state model. In fact, you'll see some quotes I'll show you later, but some recent writers, Jastrow, a NASA astronomer, confessed atheist. But he points out that he's sort of surprised at the reaction of his profession, because it's clear they're emotionally committed to a non-creation hypothesis, even though all the evidence that's pouring in is confirming the biblical view. But in any case, the steady-state model attempts to get around some of its problems, led to what's called the hesitation model. I won't bore you with that because it also was refuted in the 60s. And so this led to an oscillation model, because on the one hand it's expanding, so they tried to set up equations where it's expanding, contracting, oscillating, to try to make it, even though it's expanding, to make it have a cycle of some kind from the past. And that was quickly refuted by several things. The fact there's not enough mass, if you go through all the calculations, to justify those models, but even more important, it violates the entropy laws. Because if it's expanding, contracting, it's losing something each time, it would eventually dampen out. And so again, you are denied that approach to try to get to an infinite universe. You still have a finite universe. The current versions of the Big Bang are sometimes called the inflation model for reasons I won't bore you with. They're typically attributed to Alan Guth at MIT and others. But even there, they have to postulate for a certain period of time a force that's never been observed in the universe. That's called contriving. It's interesting conjectures. It's sometimes fun to explore, but not to take seriously. To build models on phenomenon that are postulated rather than, it doesn't prove anything. Now, I want to get into another area that is absolutely controversial among physicists. Going back a little bit, c, like E equals mc squared, c is the universal constant or a parameter for the speed of light. C is a mathematician or physicist term for the velocity of light. And up until about the 17th century, most serious physicists took for granted that light was instantaneous or its speed was infinite. Johannes Kepler, who's famous for the planetary laws, and René Descartes and others, these are very influential thinkers of their time. All believed that light was instantaneous, or the speed of light, the velocity of light, was infinite. In 1677, Olaf Rømer, a Danish astronomer, noticed that the eclipses of the moons of Jupiter were slightly different depending on how far Jupiter was from us, because there are very large orbits involved, and at certain times in the calendar, there was a great distance. The distance was larger than at other times. And by carefully taking data of the eclipses of Io, one of the moons of Jupiter, he figured out a way to measure the speed of light. And he did in 1677. And the physicists in that day were in an uproar. You know, it fascinates me because most of us, I think, will admit that we have prejudices and biases. But if you're a scientist, presumably the altar you worship at is objectivity. And yet it's interesting, if you look at a history of science, you'll find that they cling to their emotional prejudices with all the passion of any other human being in their belief structures. And even though Olaf Rømer did this experiment, it took 50 years before they accepted it. James Bradley, an Englishman, in 1729 repeated the experiments of Olaf Rømer and demonstrated the speed of light was finite, roughly 300,000 meters per second or 186,000 miles per second, depending whether you're in the metric system or the English system. When you're in physics, you generally use the metric system. But I was intrigued when we were at the Garden Tomb in Israel. The guide, who's a very this British trust that takes care of the Garden Tomb, this very British guide made no apologies for talking about the huge cistern there, which is very important for a lot of reasons. He measured it in gallons, 250,000 gallon cistern. So I make no apologies for not speaking the metric system. If God wanted us the metric system, he would have had 10 disciples, you see. The speed of light has been measured over the last 300 years by at least 163 different times by 16 different methods. One of them, by the way, in 1873 was by Michelson at the Naval Academy. He actually did it at the Naval Academy. And if you go there, you can see, they'll show you where he did it. But in any case, along comes two guys, Barry Setterfield, a physicist, and Trevor Norman, a mathematician. And they undertook to study carefully, we tried to track down the raw data for all these different experiments, as many as they could get their hands on. And as they analyzed the measurements of the speed of light over those 300 years, they came to a rather surprising and very controversial conclusion. And what I'm telling you now is by no means proven or certain or accepted. In fact, quite the contrary. I would say that 9 out of 10 physicists will laugh at what I'm going to present here because they don't accept this. And they may be right. I'm not saying they're wrong. But it's interesting. Rømer, in 1677, determined the speed of light was 307,600 meters per second, plus or minus about 5,400 kilometers per second. The error rate, because of the nature of his experimentations, the limitations of the way he went at it. In 1875, at Harvard University, using the same method, they measured it and concluded it was 299,921 meters per second, plus or minus 13 kilometers per second. In 1983, the National Bureau of Standards, using a laser technique, measured the speed of light as being 299,792.4586 plus or minus 0.0003 kilometers per second. As you look at these, the fact that the error, Rømer's error, was about 5,400 kilometers versus Harvard's 13 versus the National Bureau of Standards being a very small fraction, you notice that obviously the techniques are improving. But what's disturbing is you'll notice that each measurement doesn't even fall within 1 or 2 sigmas of the previous measurement. In other words, it appears that it's been slowing down. And that was what they concluded, and that's what they published. And you talk about an uproar. All kinds of people have been writing papers attacking their character, attacking all kinds of things. And yet, little by little, some are beginning to take them more and more seriously. Al Montgomery, a Canadian mathematician, went to a computer, analyzed their data thoroughly, and he came to the conclusion that not only is it slowing down, there's a 99.9% correlation to a cosecant squared curve, which implies that looking back through history, the speed of light was vastly faster. Now, this is disturbing for lots of reasons, because the speed of light is such a crucial parameter in atomic behavior, in living molecules, molecules that are associated with living things, and so forth. So it's a very, very fundamental thing. But again, I'm always reminded, whether you're talking about Copernicus, or whether you're talking about Romer, or the phlogiston theory of chemistry, if you look through the history of science, you'll notice that most of the major changes take a long time to gain acceptance. Now, it's interesting, if you start studying the characteristics of space itself, there's some parameters: permittivity, electrical permittivity, magnetic permeability, zero-point energy, and intrinsic impedance. These are mostly electrical kinds of measures. It turns out that if any of these properties change isotropically, that means change the same in all directions, then both the atomic behavior and the velocity of light would vary throughout the universe. This would be common throughout the universe. In other words, the speed of light would derive from the properties of space itself. Now, permittivity has not changed, but magnetic permeability has, and their product equals the reciprocal of the speed of light. There's an intimate relationship. Let's move on a little bit, leaving that enigma for the moment, and let's understand that the universe today is evolved with 4 basic forces. There are only 4 known forces in the universe: gravity, electromagnetic forces, what's called the strong nuclear force, and a weak nuclear force. They're sort of opposites in a way. Now, gravity we're pretty familiar with. That's what causes an apple to fall to the ground. That's what keeps your feet on the floor, unless you go to certain services in some places. Gravity is what binds our solar system together. This is what keeps the Earth and the planets on their orbits, and our galaxies for that matter. This also prevents the stars from exploding, and this guides, of course, the galaxies on their motion. So I think most of us are familiar with gravity. The next major, most important force is the electromagnetic force. In fact, here on the Earth, it occasionally, under the right circumstances, can overcome gravity. This is what happens when you run a comb through your hair and it'll pick up paper. Static electricity is a form of electromagnetic force. Magnetism, of course, is an example. The electromagnetic force is what holds an atom together, and it determines the structure of the orbits of the electrons, and because of that, it governs the laws of chemistry. The forms of this force can include X-rays, radio waves, microwaves, and, of course, light. These are all examples. And as I said, it can overcome gravity on the Earth, and it can dominate the other forces down to a distance that's approximately the size of the nucleus of an atom. At that point, we've discovered these other 2 forces start to be more significant. Of the 2 nuclear forces, one's called, for lack of a better name, the strong nuclear force. It's the thing that binds together the protons and the neutrons at the nucleus of an atom. And it's the balance between the strong force and electromagnetic forces that limit a nucleus to about 100 protons. See, the electrical force, if you have 2 positive particles, they try to repel. The strong force holds them together. But if you get more than 100 or so, the strong force is not able to hold them together. And that's one of the reasons we only have about 100 elements on the periodic table, 90 some odd. The energy released by the strong nuclear force is vastly more powerful than the electromagnetic force. The electromagnetic force corresponds, in a sense, to chemical energy. Dynamite, in effect, is a release of the electromagnetic force that's bonding those molecules. But the strong force is what is the source of the energy of an atom that's being split, and that's where that energy comes from. So the strong force accounts for one of the reasons that stars shine. Thus, all these forces, incidentally, turn out to be essential for life in more ways than you can imagine. I'll come to that in a minute. One last one, that's the weak nuclear force. This is the one that governs atomic instability and radioactivity. You normally wouldn't encounter it except maybe with a Geiger counter. It measures the disintegration of the heavier nuclei. It can create heat, and such as the decay of radioactive elements inside the Earth's crust or in a nuclear power plant, those kinds of things. 4 basic forces. Now, this leads to a discovery. It's called, even by secular scientists, it's called the anthropic principle. And it's the apparent design that's manifest in the universe. Paul Davies, probably the real champion of the atheistic, materialistic view of the universe, He, in his own writings, you couldn't improve on his definition here. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. I think that's remarkable, coming from one of the most articulate and widely read of the serious cosmologists. Now, I want to give you some examples, first of all, of just these forces. We talk about gravitational coupling. And I'm going to visualize a star with a planet. The star we have in mind, of course, is the sun. The planet is the Earth, but I'm going to deal with it in abstractions here. It turns out if the gravitational constant, coupling constant, was a little stronger, then all stars more massive than our sun, more than 1.4 times, would burn too rapidly, too inconstantly to maintain life-supporting conditions in our surrounding planets. If it was just a little weaker, all stars would have less than 0.8 times the mass of the sun, and there would be no heavy elements in these things. If we look at the electromagnetic force, the coupling constant that measures it, if it was weaker, molecules for life would cease to exist. If the electromagnetic coupling was a little stronger, again, for other reasons, molecules for life would cease to exist. If you look at the strong force, if it was slightly weaker, the multi-proton nuclei would not hold together. Hydrogen would be the only element in the universe. If it was slightly stronger, nuclear particles would tend to bond together more frequently and more firmly. Hydrogen would be rare in the universe, and the supply of various life-essential elements, heavier than iron, would be insufficient. The weak force coupling, if it was larger, there'd be no helium, no heavy elements. If it was weaker, it would all be helium, and there'd be an overabundance of the heavy elements. They discover that these four couplings, the gravitational coupling constant, the electromagnetic coupling constant, the strong nuclear force coupling constant, if you vary these by one part in just a fraction, life in the universe would be impossible. They're all exactly where they ought to be. And that's what bothers some scientists, because it's as if somebody ran around and very carefully tuned it. See, most of us sort of figure, well, gee, if the numbers were different, life would show up, but in some different form. No, it's not that simple. Boy, do they wish it was. No, these probabilities compound and compound and compound. Another thing, the ratio of the electron to proton mass. If it was larger, molecules would not form, life would be impossible. If it was smaller, molecules would not form, and life would be impossible. Take your pick. It's exactly where it needs to be. One part in 1,836 parts, I believe. So we could list, I could bore you on and on with this. We've gone through the first few, but there's also a bunch of others that I'll spare you, because I'm probably losing some of you already. Let's shift and look at, instead of the tiny place, let's go take a look at the solar system. Our parent star, the sun, if its mass was greater, the luminosity would change too quickly and it would burn too rapidly. If it was less, the range of distances appropriate for life would be too narrow. Tidal forces would disrupt the rotational period for a planet of the right distance. If you start trying to make an imaginary universe to figure in our present laws of physics, you'll discover all these things start to interact. If our sun was a different color, a little redder, photosynthetic response would be insufficient. If it was a little bluer, same thing. In other words, it's exactly where it needs to be to have the photosynthesis that we all depend upon. The distance from the sun, if it was a little further, it would be too cold for a stable water cycle on the planet Earth. If it was any closer, it'd be too warm for a stable water cycle. It's exactly that distance for a stable cycle. So we can talk about mass, color, distance from the Earth, some others. Let's go on, talk about the Earth itself. The surface gravity of the Earth. If it was stronger, atmosphere would have too much ammonia and methane. If it was weaker, the atmosphere would lose too much water. See, however you start playing with these things, scientists know enough to realize you start adjusting any one of these, they all interact too much. Thickness of the Earth's crust. If it was thicker, it'd be too much oxygen would be transferred from the atmosphere to the crust. If it was thinner, volcanic and tectonic activity would be too great. If you go to the Earth's rotational period, if it was longer, the temperature differences would be too great. If it was shorter, the atmospheric wind velocities would be too great. Axial tilt. If it was greater or less, the surface temperatures would be too great. The albedo, that's the reflectivity of the Earth. Of all the light that hits the Earth, some of it's reflected. Well, if it was greater, we'd have a runaway ice age would develop. If it was less, a runaway greenhouse effect would develop. The Earth's magnetic field. If it was stronger, electromagnetic storms would be too severe. If it was weaker, there'd be inadequate protection from hard stellar radiation. CO2 and water vapor levels. If it was greater, a runaway greenhouse effect would develop, and if it was less, the greenhouse effect would be insufficient. You need just the right amount. That's exactly what we've got. And this may sound familiar to you. Let me show you an example. You've all heard about this one, ozone level. If it was greater, the surface temperatures would be too low. If it was less, the surface temperature would be too high. And there's also too much ultraviolet radiation in the surface. By the way, before I go on, it interests me every time you have one of these ecologists come and tell you that, gee, if the ozone layer changes 0.1%, we have cosmic doom. How many of you have heard that? Huh? Well, turn that over. If that balance is that critical, how did it get there by accident? You see, it isn't as if there's just one. There are dozens of these. And some of these are cannot be off by more than 1 part in 10,000. 1 part in 10,000, if it's off, life ceases to exist. And there are hundreds of these kinds of things. Now, the earth factors, there's a whole list of these. I won't go through all of them here. We've just taken a few to give you the flavor of them. There's also a whole series of things that have to do with the universe, and these are not really comprehensible unless you've done some study in terms of the life cycle of stars and the physical dynamics within stars. I won't go through all that here. But again, you have total comprehensive entropy and mass considerations, which, if they're different, scientists today believe the universe would cease to exist. All of this, to get to the point, confirms the original cosmological argument. Either the universe created itself, or it was created by a pre-existent first cause or creator that transcends the constraints of time and space. You're still faced with the same choice that faced Al-Ghazali and Thomas Aquinas and others 1,000 years ago. The difference is, in the last few hundred years, we have discovered so much about science, and all these discoveries point in the direction of the biblical model. You'd never guess that by the way it's presented by people who are clinging desperately to some construct that will allow them to duck the implications of a finite universe that is decaying, that had a creator, because if it had a creator, he had a purpose, and if he had a purpose, there's going to be some accountability and responsibility involved. And that's the rub. Now, Robert Jastrow has done a lot of writing. He's a NASA astronomer, professed atheist. He says, Now we see how the astronomical evidence leads to a biblical view of the origin of the world. The chain of events leading to man commenced suddenly and sharply at a definite moment in time in a flash of light and energy and so forth. And there are dozens of quotes like this. I just picked one. But I'd like to shift gears a little bit and show you another dimension that is, I think, even easier to understand and even more irrefutable. We've talked about cosmology. We've talked a little bit about physics and some other things. We'll be talking about biology and some of the other sessions. I'd like to touch briefly on a topic that we'll also explore more substantially in a subsequent session, the information sciences. And the information, as a field of science, the information sciences is of relatively recent vintage. So 40, 50 years would cover Shannon, Wiener, and the rest. So the information sciences clearly demonstrate that skillful, careful design is not only evident, but system engineering rules out chance as a rival conjecture. And what do I mean by that? The present view of scientists and the secular mind in general is that somehow these things all just happened. Well, this occurs especially in biology, that they somehow get around the preposterous hypotheses they advance by saying it happened, there's so many billions of years, they need this long time to mask the absurdity of it all. Well, now let's wait a second. Many of these probabilities they deal with are 10 to the 100, 200 or larger numbers. Well, one of the questions, I remember I was talking to one of the scientists at Livermore. They easily bandy about these numbers. 10, somehow, I won't bore you the context of it, but the 10 to the 18th came up. And I says, boy, that's interesting. That's more seconds than there are in the history of the universe. I remember he looked at me, one of Dr. Teller's right hand that we were working together on a project. He turned to me startled. I said, what do you mean? I said, well, you brought it up. He said 10 to the 18th. You would tell me, I suppose, that the universe is 15 billion years old. Well, yeah, I guess so. He says, well, take your calculator and figure out how many seconds that is. That's only 10 to the 18th seconds. And he was stunned. Not that he wasn't familiar with these large numbers, but it never occurred to him that, you see, these numbers get very, very big. So if you say to yourself, gee, what's the average lifetime of living organisms throughout the history of the universe? If you say the average lifetime is no more than 1 second, an absurdly small number, then the maximum generations are 10 to the 18th. You say, well, maybe because of microbes way early or something, their average lifetime was 1/1000th of a second. Rather absurd, but okay, that's only 10 to the 26th. So it turns out that, first of all, if you want to accept these hypotheses, there wasn't time. Secondly, you say, well, how many tries? If you're going to try to do something by accident, you're going to somehow have random atoms come together to make a piston and a cylinder that fit within so many thousandths or whatever, by accident. That's, of course, absurd for a lot of other reasons we'll come to. How many tries do you have? Well, if I had 1 try for every atom in the entire universe, that's only 10 to the 66th. If I had one for every particle in the universe, that's only 10 to the 80th. See, these numbers get very, very big. In fact, within the field of physics, since a mathematician would say that nothing's certain, nothing's impossible, it's all a question of probabilities, you get into the problem of boundary conditions. When does something become unlikely enough to be considered absurd? And they arbitrarily use the 10 to the minus 50 as the boundary limit. Anything with a probability of less than 1 part in 10 to the 50th is considered within laboratory science as absurd. Well, that's kind of interesting because that would rule out most of the stuff that's in your high school textbooks. But now, there's a concept that derives from the second law of thermodynamics. We've talked about it so far in a physical sense of the fact that all things are inefficient. In an engine sense, it means that no engine is 100% efficient. It has some loss. And the loss goes to the ambient temperature of the universe, and eventually it'll all be uniform in theory. The same mathematics, the same concept, also relates to information. And that's where you get the term entropy. It's used in thermodynamics, but it's also used in information. Entropy is like a synonym for randomness. Left unaided from the outside intellect, things degenerate. And what I mean by that is, take for an example, your closet at home. You will spend a half of Saturday cleaning it up and getting it all organized. What will it look like a week or two later? Or it could be your garage or your locker at school. You notice that things seem to deteriorate. It takes energy, effort, thought to put them in what you and I call order. You discover every place you look in every field of science, things are going from order to disorder. You discover the universe is winding down not only thermodynamically, but that's really just a reflection of a more basic law. And it's usually called the second law of thermodynamics, or the entropy laws. But again, it's an evidence that something is wound up and then it winds down on its own. We wind it up, so to speak, by inputting to that closet or whatever our order, our outside intelligence. There is a concept in information of a contrast. Engineers will speak of signal and noise. If you're listening to a receiver, that which carries information, intelligence, that to which you're trying to get is called signal. All that other stuff that gets in the way is that random noise is called noise. Signal and noise are opposites. In the same way that order and chaos are opposites. Order is, most of us I think understand what order is. I think most of us would understand what chaos is, and I'm not getting into the moment this field of mathematics that's emerged about that. There's the concept of direction versus what's called a random walk. The opposite of direction is, mathematically, one of them is a random walk. The concept of control as opposed to anarchy. The concept of music as opposed to cacophony. And that's a hard example to use in modern music, so I'll keep moving. Information is called by the mathematicians negentropy, negative entropy in effect. And of course, the ultimate one that you and I are wrestling with is design and chance. Something can happen randomly, or something can happen by design. And we're going to explore this in detail in another session, but I want you to be sensitive in the first place, because there's another concept of design that we want to be sensitive to, and the hierarchy of design. One of the simplest things to design is what's called an open-loop system. A wristwatch on my wrist is an open-loop design, not trivial. If you were a spaceman stepping off the first spacecraft to land on Mars, and you took a step or two and you found in the sand on Mars something that had a watch, that had a date, mentioned the time, whatever, would you believe that that watch happened there by accident? Would you believe that random molecules somehow assembled them? Of course not. That's a variation of the famous Bishop Paley watch. The point is, certain things evidence design. If you find a piston in a cylinder, it's not very likely that happened by accident. Someone went through a lot of trouble to do that. If a mechanical watch with its cogs and gear, evidence is design, intelligence, a mind, not random accidents. That's the simplest form of design. Let's go one step higher to show you what I mean. The next idea is what's called a closed-loop system. Let me talk about the power steering on your car. Very complex system. And I suspect if you've got a group of mechanical engineers together, probably only 1 in 100 would know what a Nyquist diagram was to get that thing resolved properly so it operates the way it should. Closed loop system. A whole level more complex than an open loop system. But let's go one step further. Let's talk about adaptive systems. These are systems that not only are closed loop, but they will sense the environment and respond accordingly. Example is your anti-skid brakes that will sense the coefficient of friction and make adjustments. Then, of course, we get to our age that we're so proud of, is we're all just going to lump together called intelligence machines, computers. Now, the first thing about a computer is it processes language. Now, anyone that has any brain in his head realizes that if you're going to have an engine that processes language, you've got at least 2 design problems. You've got to design the language and you've got to design the machine, and they can't happen by themselves. They've got to be very closely coordinated. Anybody with any sense knows that. So we discover our bodies have a DNA code, that every cell in your body has a code that contains your entire genetic history. It turns out it's an error-correcting digital code embodied in a 3-dimensional environment in which its very embodiment becomes the engine for its deciphering. And those engines change function as they need to, as their roles change. The most complex thing you can imagine. No way could it happen by chance. And I'm not saying it's improbable. I'm saying it's absolutely impossible. But let's go one step further. The next step in machines would be to have self-diagnostic machines. Machines that not only work, but they can tell when they're ill. We have very primitive ways. We start at that with parity checking and some things in certain computers. But it's very primitive compared to what's going on in your body. But let's go one step further. After self-diagnostic machines, you could have in concept self-repairing machines. We don't have any. No serious ones. And yet every system in your body is designed to be self-repairing to some level. Let's go one step further. Self-reproducing machines. See, when you look at the hierarchy of design as an information scientist would, the idea that we as machines have happened by chance is the most absurd hypothesis you could put forth. The ancient cultures created idols to worship instead of worshiping the living God. And we look back at those guys and say, weren't they stupid? And yet, in our culture, we've invented the most absurd God of all. We don't attribute the creation to some idol or we attribute it to nothingness, randomness. I cannot imagine dreaming up a more insulting allegiance to assault the living God who went so far not only to create us, but to redeem us in the first place. But let's move on. Complex systems cannot develop gradually through non-functional intermediaries. Having something that doesn't quite work will not cause it to survive. And many examples of that. And you have to have perfect, multiple, simultaneous adaptation of all the interacting systems as a prerequisite condition for functionality. Any design engineer knows that. And so organization reveals external information input, either pre-programmed or by active coordination. Which leads, of course, to the biblical cosmology. The 20th century sciences have finally caught up to what the Bible is saying all along. We have a finite universe, it's decaying. It was built by a transcendent creator that is not only outside it, but can enter it when he likes. And of course, we're going to get to the uniqueness of the biblical source of information. One thing I think is fascinating, Nachmanides, I mentioned him earlier. If you read his commentary in Genesis chapter 1, you discover he came to a strange conclusion about Genesis chapter 1. Over 800 years ago, he concluded that the universe has 10 dimensions. 4 of them are knowable and 6 are not knowable in his vernacular. And if you read the advanced literature in particle physics today, you know that scientists today believe that we live in a 10-dimensional universe. 4 dimensions are measurable. In fact, they're quantized. 6 of them are curled in less than 10 to the minus 33 centimeters, and therefore are inferable only by indirect means. And if you start reading that and you come to grips with that, it's interesting that with all the billions of dollars we spent on cyclotrons and atom smashers, what have you, that we've come to the same conclusion that Nachmanides did by just doing his homework on Genesis chapter 1. Now, one of the things that lies behind all this isn't just an exercise in physics or what have you. We as a culture have determined to abandon truth. The failure of objectivity in science startles me. As one who has aspired to and been involved in various ways in the scientific and engineering world for a better part of, 40 years or more, it startles me to realize, really come face to face with the fact that science is no more objective than any of the other pursuits of special interests on the landscape. In fact, this abandonment of objectivity in science has led to value relativism. Because if we're all here by chance, then all values are relative. And that, of course, has resulted in the reduction of human dignity. It has resulted in the moral decay of our society. It has led to the fallacies of Marxism and socialism, and which in turn has as its goal subjugation, slavery, and bondage in all the nations across the world, and is actively pursuing in this country. And that derives from the misconceptions that have been perpetrated on our society through non-objective science, ill-guided educational policies, and lack of diligence on the part of you and I. Romans chapter 1 verse 20 says, "For invisible things of him from the creation of the world are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that we are without excuse." This says that even without the Bible, God can hold you accountable for knowing who he is, at least to some level, by just doing our homework, by looking around us. Now, the ultimate challenge was put by Joshua. He expressed it, "Choose this day whom ye will serve." There is a God called chance, who I regard as the most insulting God of all, nothingness. Or there's a transcendent creator who demonstrates that he transcends our universe, that he is beyond the constraints of time, space, matter, energy, what have you. Now, most of us, as we think about what I'll call the geometry of eternity, again, it's a byproduct of this linear mentality. We sort of see ourselves right here at the now. Behind us is the past. Ahead of us is the future. But it's interesting, Dr. Albert Einstein, I forgot to make a slide up for it, but Dr. Albert Einstein, it says that the one thing that those of us that believe in physics know is that the past, present, and future are nothing more than a stubbornly persistent illusion. And we'll talk about that in one of the subsequent sessions when we'll get into particle physics and the boundaries of reality, that scientists now have discovered that reality is not local. And we'll come into some of those things. But the point is, you and I tend to think of past, present, future, and we're in the present. The past is a memory. The future is a hope. Our connection, we tend to think of eternity as maybe the ultimate future. We tend to think of the future out there. And one of the implications of all that we've talked about today is your connection with eternity is now. Think of eternity as another dimension. I just portrayed it here on the slide graphically as a two-dimensional plane cutting this orthogonally. Your connection with eternity is right now. And the question is, what are you going to do about it? It's hard to deal with some of these topics without getting into mathematics and other background. At the same time, what I was hoping to accomplish to serve as an introduction to the sessions that are coming. We're going to explore the fields of biology, but the exciting opportunity for you and I today is that the fields of science, honestly considered, demonstrate that we are in a universe that is described and anticipated in the biblical view, that we are indeed here right now at this point in time as the result of an active, diligent, skillful Creator who not only placed us here, He didn't do it without a purpose. And He's given you something that is terrifying. Your free will. He's put you in a situation where your eternity is determined by the choices you make. Not by how much you know, not by, in fact, anything, but your choices, your attitude towards Him. And your connection with that eternity is right now, at this point in time. The eternal now, as it moves forward. The now. One of the things we're going to bring out in subsequent things, that the real you sitting there is software, not hardware. Has no mass. The real you is resident in an environment, a body. And yes, I know it's also subject to the bondage of decay. Some of us are more conscious of that right now than others. But the real you is software, not hardware. And software has no mass. Therefore, it has no time. And every one of you in this room are eternal, whether you like it or not. That's not good news if you're not in Jesus Christ. So one of the things that Mark and I are prayerfully hoping is that you will continue to join us in these survey discussions and hopefully gain a little clearer insight as to where we are and the universe around us, and most of all, how it points to and glorifies the Creator that brought us here. I'm going to have you stand in a moment for a closing word of prayer. But before I do, I want to challenge you. If you've come in here with the slightest doubt as to what would happen to you if you got hit by a car on the way home or suffered a heart attack or whatever, fill in the blank. If something happened to you to end life as you now experience it, do you know, not guess, do you know where you'd be? The exciting news is that there's no reason to have any doubt about your eternal destiny. Because that Creator that put you here, that created this universe in the first place, for a finite period of time, not forever. It hasn't been here forever. It won't stay here forever. Heaven and earth will pass away. And from a lot of evidence, it's a lot closer now than most people realize. This same Creator is transcendent of time and space. So what does that mean? That He's outside of it? Not that alone. He also can enter it at will, and He has. He has chosen to substitute His eligibility for yours. He has a destiny for you that's so utterly fantastic, even what we know about the universe pales in comparison to what He has in store for us. The problem is we can't earn it. It is so fantastic that we can't qualify for it. We've incurred a genetic defect that prevents that, called sin. But He knew that in advance. He knew that before the Big Bang, before whatever, before the foundation of the world. And He provided His redemption in the Son, Jesus Christ, and it's available for the asking. You may say, gee, Chuck, I'm not ready. You can't be. You never will be. Before you leave this room, if you're not sure of where you're headed, you can, in the privacy of your own will, seal your eternal destiny. When we stand for a closing word of prayer, I'm going to invite you quietly, in the privacy of your own will, to declare yourself before the throne of the transcendent Creator and ask Him to make His redemption available to you. And He'll take it from there, if you're serious. If you're serious.